Hello, uh, hello everyone. So welcome to the ninth week session of the statistical mechanics course. So this is a TA session. I am Parashar and I am a PhD student in physics at IISc Bangalore. So so this week we'll be discussing problems on Fermi-Dirac statistics and Fermi gas mostly. So um, yeah, let's get started. Okay, so first of all, before we do some examples, problems, it is useful to uh, revise some of the properties of these Fermi integrals, which appear often during the calculation of various properties uh, of uh, the Fermi gas. So the integral is as follows. So it is this is the integral. Uh, so this integral for various values of n appears uh, for or it appears in the expressions involving various quantities like the number of particles, energy, pressure, and so on. Where the value of n for all these different quantities is different. So we'll be interested in general integral of this kind. So let's look at some of the properties of this integral. So, so first of all, this has uh, uh, this function or this integral has a series representation. So we can write this as yeah. So we have just multiplied with some factor, nothing more. So now the idea is that we can do a series expansion of this expression in the denominator, or so we can use 1 by 1 plus y. Yes. Yeah, so so this converges for uh, mod y less than 1, but but as a uh, yeah, but as a sum I mean we can we can formally write this and see uh, what is what is the expression we get. So here y would be this, and let's then expand it like this. So there's a set here. So this is in some which is alternating, so it looks like 1 minus y plus y square minus y cube and so on. Yeah, so we have expressed this expression in the denominator using this sum, this infinite sum. Now, uh, yeah, so let's bring out the sum outside. So that will become 1 by gamma n sum over n from 0 to infinity and integral. So we have yeah, so uh, we have taken the sum outside, and so we have this integral here. Uh, yeah, so we can first of all we can just write this summation as sum m going from 1 to infinity minus 1 whole to the m minus 1 z to the m e to the minus mx. So we have just uh, re uh, redefined the dummy variable m, and this integral that looks like an integral involving the gamma function. Uh, uh, so indeed, so we can make a change of variable. Let's say t is equal to mx. Then this would be integral 0 to infinity dt t to the n minus 1 e to the minus t times 1 by m to the n. So, and this function, this integral is the definition of the gamma function. So this is gamma of n. So finally, once we put this in here, we see that this Fermi-Dirac integral Fn of z is equal to sum over m going from 1 to infinity minus m to the m minus 1 uh, z to the m by m to the n. So this is a infinite series uh, uh, form of this function. So that looks like um, z minus z squared by 2 to the n plus z cubed by 3 to the n and so on. So, so this expression would be useful uh, in the high temperature expansion of the Fermi-Dirac gas. So this will be useful when z is much smaller than 1. So this would be the high temperature expansion. Okay, so now that we have obtained this infinite sum expression, let's also look at the derivative of this function with respect to z. Yeah, we'll be using that in the problems today. So, so the question is, what is the derivative of this function with respect to z? So that is going to be yeah. So now that will be equal to m1 to infinity minus 1 whole to the m minus 1. Z to the uh, yeah, z to the m. We can write z to the m by bringing down a factor of z by m to the m minus 1. Yeah, m to the m minus 1. Yeah, so this we see this is related to fn minus 1. So it has the same form of this. We've just uh, we just have n minus 1 in place of n. So this is nothing but fn minus 1 of z. Okay, and one more one more uh, important property of this function is the uh, expansion in the high z limit. So expansion of this in z going to infinity limit. So this has an expansion in terms of log z. So yeah, so let me just write the first and of course the next leading term in this expansion. Yeah, so this derivation will take like a long time. So I think it has already been done in the lectures. So let me just mention that. So this fn of z will be equal to I think yeah log z whole to the n by gamma of n plus 1 times 1 1 plus y squared by 6 into n into n minus 1 by log z whole square. I think this is correct. Uh, Let me check. Yeah, that's fine. Yeah. Yeah, so this is the leading or this is the leading order of contribution. Uh, okay, so uh, this is the expansion for the Fermi integral when z is very large in terms of log z. Okay, and these will be very useful for I mean this particular expansion in the z high in the z going to infinity limit will be useful uh, to calculate the properties of low temperature. Uh, I mean, like the low temperature properties of the Fermi gas. So this will be useful. So when T is very uh, small, I mean, when T is much smaller than the Fermi temperature, or when we are near zero temperature, this will be useful. Okay, so yeah, let's get started with some problems. So this was just some quick review of this function, the properties of this function. Okay, all right. So oh, sorry, I'm sorry. The Yeah, yeah. So I was just uh, like writing this formula, and then I've just realized that my screen was not uh, visible. Anyway, yeah. So yeah. So now let's get started with the problem. And so we have an ideal Fermi gas. So this is a non-interacting Fermi gas in d dimensions. So so in the lectures we learnt about the Fermi gas in three dimensions. But I mean, we can also think about Fermi gas in some other number of spatial directions. For example, it could be in two dimensions. Gas could be restricted to move in two dimensions. So that could be an interesting case. But so for the sake of this problem, let us keep d to be some general number, integer, and the single particle uh, states have energies uh, given by this. So the the energy of a state with momentum k is given by some constant of proportionality alpha times mod k to the power m. So in the non-relativistic case, m would be 2. In the ultra-relativistic case, you have learned in the lectures that m is equal to 1, right? Okay, so uh, now the question is about finding the relation between pressure and energy density. So that means energy per volume. So what is the relation between these two? Okay, so we can proceed with the formalism. I mean, we can proceed in the grand canonical formalism of the problem, uh, and try to see uh, what the relation is. So let's say we have the system in contact with some temperature path at T and particle path or particle reservoir at chemical potential mu, and uh, we want to write the partition function for this. So since this is a non-interacting problem, we can simply write the partition function for each single particle state. So let us denote with set of the set I, the set of all single particle states available, and the specification Ni, uh, with each Ni being 0 or 1, gives gives a specification of the state of the system. It's a complete specification of the microstate of the system. Uh, yeah, because these are fermions. Recall, so these are uh, not distinguishable particles. So only the specification of Ni is required, is enough, and for a single uh, for a single state, the partition function would be just Yeah. So there are two choices. Either it is occupied or not. So that means the partition function is this. So this will be EI. Okay. And the full grand canonical partition function is, which is product over I. Okay. So uh, now immediately we can write down the pressure from this. So we know that in the grand canonical ensemble, uh, pressure is given by this. So PV is just the negative of the grand canonical potential, which is minus kBt log Z. Yeah. So phi would be minus kBt log Z, and since we have minus phi here, that would be kBt log Z. So pressure would be equal to 1 by V kBt. Log Z would be, log of this product. So that would be sum of logs. So that would be sum over I, log of 1 plus e to the minus beta times ei minus mu. Uh, so this is the pressure, and we also need the energy. The average value of energy would be sum over the single particle states, the occupation of a single particle state times the energy of that single particle state. Right. So we know that the average occupancy of a single particle state is given by the Fermi function, which is this. Okay, so far, like this is all very general. I mean, this is true for any non-interacting Fermi gas. So now uh, let's make use of the fact that we have a like a continuum set of states, uh, and we can replace these sums with integrals. So the expectation value of energy would be some integral over energy, the possible values of energy, and we have to look at the number of states in this interval, the density of states, G of E, times E, divided by E to the beta times. And similarly, we can write the pressure using this. So PV will be equal to kBt times. So this factor is like the number of states. Uh, so this factor appears when we replace a sum with an integral. And yeah, so far still this is very general. I mean, we can write this for any non-interacting Fermi gas. Now let us look at what information in the question will affect what quantities in these equations. Okay, so So recall that it is a system in d spatial dimensions, and the dispersion energy is given by k to the m. Okay, so what does that mean for the density of states? So in the last week we did this. We have solved this question of finding the functional dependence of the density of states on the dispersion relation and the number of dimensions, right? So if you remember, g of e, g of e goes as some constant times e to the d by m minus 1. So this is how the density of state depends on the dimension and the dispersion. So for the case discussed in the lectures that we have learned, so d is 3 in 3 spatial dimensions and m is 2. So there the density of states depended as square root e. Okay, but last week we saw that uh, like for a general D and M, this is the dependence. So now we can use this here. I mean, we have to use this here, right? So let's put this in both of these equations. All right. So and at the same time make this change of variable. So yeah, this is again a very standard trick to uh, to get the functional dependence of certain things when you have an integral. So it is always a good idea to uh, convert a dimension-full integral, like where the integration variable is a dimension-full quantity, to an integral over a dimensionless variable. Yeah. So here naturally we have this uh, beta which gives us a scale of energy to do this. So let's say that x equal to beta e is the change of variable will do. Uh, yeah, I mean this is this is done uh, like even in the standard like three-dimensional gas we have learned. Uh, so this is done so that the integral is over, like I said, a dimensionless quantity. So yeah, anyway, so after doing this, we see that so this will bring down a factor of beta to the d by m plus 1 after making the change of variable, and we'll get this proportionality constant A, the proportionality constant that is in the density of states. So that is of course there here, and the integral is integral dx x to the d by m. So there is x to the d by m minus 1 from the density of states, and of course there is the factor e here, which gives another uh, which will add to this exponent that was there. So finally, we have z inverse e to the x plus 1, where z is the usual definition, it's the fugacity, e to the beta mu. Okay, so we have this expression for the energy. So let's keep it. I mean, let's leave it there and come back to this later while we also look at the expression for pressure. Yeah, so doing the same thing, I mean, doing this change of variable, we see that PV will be equal to KBT, which is 1 over beta, times, so we will get a factor of 1 over beta to the power d by m from this. And this is integral x to the d by m minus 1 log of 1 plus z times e to the minus x. Yeah, so of course, this limit is from 0 to infinity. Yeah, so this is the expression for pressure, or rather, pressure times volume. Okay, is there any? All right, uh, so these look like different integrals, and we have to relate, these two quantities on the left-hand side. So what we can do is we can do integration by parts on the second integral. So if you do integration by parts, and take this as a function we take a derivative of, then this becomes log of this quantity times this between 0 and infinity minus integral so we need to take the derivative of this, which is and finally we have x to the d by m by d by m. Yeah, so if you look at this first term, both the limits are 0. So this x going to infinity limit is 0 because so that just becomes uh, so this looks like log of 1 plus y for y very small, and then we get an exponential multiplied by a polynomial or some power of x, like an exponential of minus x multiplied by uh, some power of x. So that goes to 0 at infinity, and when x is 0, it is obviously 0. So this term is simply 0. So what we then get is A by beta to the t by m plus 1 times m by d integral 0 to infinity dx x to the t by n divided by z inverse e to the x plus 1. Yeah, so this integral is exactly the integral we have here. We have in the expression for energy. So yeah, indeed, we can just relate these two quantities up to some factors. And that factor is simply this m over t, right? So PV will be equal to m by d times expectation value of energy. So for d is equal to 3 and m equal to 2, we have this PV is 2 by 3 e. But for, yeah, so this checks out. And for a general m and d, this is the relation. Or you can express this also as pressure being m by d times of the energy density times the energy density. Yeah, so this is something which is true at all temperatures. So this is an exact expression for non-interacting Fermi gas. Uh, so you'll uh, so you would have remembered that even in the classical ideal gas, this relation was true at all temperatures. So when we uh, now study the quantum gas with Fermi particles, of course, like a lot of things change. The equation of state changes, and like at low temperature, the physics, everything drastically changes. But this relation of like the relation between the pressure and the energy density, and this factor, that remains exactly that, like at all temperatures. Okay, yeah, so that is something to uh, make a note of. Okay, all right, so let's move to the next problem. Okay, I think there is one more part in this question. Uh, yeah, so find the degeneracy pressure for this gas. So let me say this is a big part. So at t equal to 0, we have a filled Fermi C until some value of energy, the Fermi energy, and uh, and all the single particle states above that energy are not occupied. Uh, so we have a non-zero pressure at zero temperature. That is called the regency pressure. Uh, so yeah, let's calculate what that would be for this Fermi gas. So that pressure would be, I mean, we can just write this as the so that degeneracy pressure, the pressure at T equal to 0, would simply be M by D times uh, Yeah, the expectation value of energy at zero temperature divided by volume. Yeah, so if we can calculate this the the energy at zero temperature, like ground state energy at zero temperature, then we can also calculate the pressure. So yeah, so now we have to calculate this ground state energy at zero temperature. Okay, uh, so we are considering dispersion in which the single particle energy depends only on the magnitude of the momentum. So so if you look at like the contours of this function, uh, let me write this again. So the single particle energy uh, E of k, E of k bar is alpha mod k to the n. So the constant energy contours would be spherical, right? So in the k space, if we were to imagine uh, a bunch of states, I mean, so that there are these finely separated points, which are the k values uh, that the single particle states are labeled by. So there is this grid in the k space, uh, like we discussed last week also, and since the energy depends only on the magnitude of k, so if you want to ask what is the set of all states below a certain energy, so that would look uh, uh, like a sphere. I mean, like that would be enclosed by a sphere. So we have some Fermi momentum kf and E of kf is the Fermi energy EF, and at t equal to zero, all states below or let's say all states with energy less than EF, these are occupied, and the rest are not occupied. And yeah, with energy, right? So uh, we can then just calculate the total energy as the sum of all these single particle energy states which have been filled, right? So this energy is then integral 0 to EF dEg of E times E. So this would be the total energy of the system at zero temperature in terms of the Fermi energy. But what is Fermi energy? I mean, we can also calculate the Fermi energy in terms of the density. So we should demand that the number of particles, the expectation value of number of particles is what we want. So like we discussed many times, this is the like the prescription of the grand canonical ensemble. Uh, the number of particles is not fixed, but we can demand that the expectation value or the mean value of the number of particles uh, is what we want, and we have to choose a mu, the chemical potential, such that this happens. So at t equal to 0, that means finding a suitable Fermi energy, filling the particles up to certain energy, so that we have the correct number of particles, right? Okay, so yeah, so now yeah, let's look at yeah, let's at this integral. So g of e has this form a times uh, e to the d by m minus 1. So that would be, yeah, so that would be the this integral. Yeah, and so this factor A in the density of states, so remember that has a volume factor in it. So the density of states is proportional to the volume of the system. So if we go back to uh, our uh, our density of states expression, yeah, so we wrote it as g of e is equal to a times this e to the d by minus 1. So this a constant of proportionality has itself has a proportionality factor v, volume. So let's say this a is equal to v times some little a, some constant which doesn't involve the volume. So that means n by v, the density, is equal to this, or Fermi energy we can write in terms of the density like this. Yeah, so note that we have not written some explicit expressions for this proportionality constant A. Yeah, I mean it can be done. So we derived this proportionality constant A in the last week's session. Yeah, so we can also include it if required. So just a quick comment so that there's no confusion. So we are defining the proportionality constant A as g of e is equal to a times e to the d by m minus 1. So we know the density of states should have the dimensions of 1 over energy. So A should have the dimensions of e to the minus d by m. Just so that there's no confusion. So this proportionality constant is the dimensionful quantity. Uh, and this little a is also dimensionful. Little a has dimensions of, yeah. Okay, so yeah, so we have found the Fermi energy in terms of the density, and now we can find the total energy by doing this integral, right? So the Fermi, I mean, the the total energy would be integral 0 to EF A times this. So yeah, we have uh, like the exponent in the integrand is more than the previous by 1. So that means this is going to be equal to, yeah, so this is the Fermi energy. I'm sorry, this is total energy. And the Fermi energy has an expression here in terms of the density. So we can substitute that here uh, to get the expression for the total energy in terms of density. And finally, we can use this relation between pressure and energy density to find the pressure. So pressure is 2 by 3 times E by V. So that is going to be equal to, yeah. So where EF is given by this the expression in the previous page. All right. So okay, so let's move to the next problem. Uh, yeah. So now let us look at another thermodynamic quantity, the heat capacity for this gas. And the question is about expressing this quantity, the heat capacity per particle, in terms of the Fermi-Dirac integrals that we have discussed. Yeah, so let's do that. So we can quickly copy the result that we have written here for energy. Yeah, so let me just copy this and yeah, so we can start with this. We have an expression for the energy, so we have to calculate the heat capacity, right? So we can express this in terms of the Fermi function. So this is nothing but this integral is nothing but f d by m plus 1 of z. Yeah, so this is the expression for energy. So when we take the derivative with respect to T, temperature, of this quantity to calculate the heat capacity, you can see that we will be required to take the derivative dou z by dou t. Yeah, so we'll have to calculate this uh, derivative. Yeah, so so let's take the derivative first, and then okay, we can think about calculating the derivative. So so this quantity del E by del T will be equal to is A. So this is nothing but kBt raised to this power. And all right. So this would be kb times kBt raised to the power d by m times d by m plus 1 times f d by m plus 1 of z. Yeah, so we have taken the derivative of this first term, and then now we have to take into account the other term. So it is dou by dou t of this quantity, f. So you can see it is dou by dou z of f d by m plus 1 times dou z by dou t, constant volume. Yeah, so this derivative is at constant volume, right? So we have to calculate the heat capacity at constant volume. Yeah, so like we anticipated, we will have to deal with this term, dou z by dou t at constant volume. So now we'll have to look at the particle number equation for this, right? So we are not changing the number of particles. So let's stop this calculation for a moment because we need this quantity. So let's go and get this. So the number of particles is, we know it's integral. I think, have you already written an expression for this? Uh, yeah, anyway, so yeah, it's just going to be integral 0 to infinity d of e g of e by, yeah, so which is going to be equal to d by m minus 1. Yeah, so now we can just do this change of variable x is equal to beta e to find that. Yeah, so of course this is an integral of the kind we have noted. So this is f d by m of z. This is the expectation value of number of particles. So note that this a has a factor of volume. So now let's take a derivative of this expression at constant volume with respect to temperature, right? So the number of particles is fixed, the volume is fixed. So we can write this as f d by m of z is, beta to the d by m, so that would be 1 by kbt. So dou f by dou, uh, yeah, so if you take a derivative with respect to temperature, you'd get dou f by dou z times dou z by dou t will be equal to, so we can write this as times, yeah, so this is what we'll get for dou z. This is what we get on the right hand side. So now what we can do is to uh, use the property that we discussed at the start of the session, uh, which relates the derivative of the function f with respect to z to the function f labeled by one index lower. So this would be f d by m minus 1, right? So this would be minus d by m, n by a, beta to the d by m by t. Yeah, if I got this right. So finally, dou z by dou t would be this divided by f d by m minus 1 of z. So we can now put this in here and divide with the number of particles. Okay, yeah, so this is like tedious calculation, but yeah, so uh, hopefully, uh, yeah, so hopefully it'll uh, help ourselves familiarize uh, with manipulating these integrals and such stuff. Yeah, so CV by n is what we need. So let's start writing this finally. So CV by n kb will be equal to, we have to divide this first term by n kb. So n is this, we have this for the n, for the number of particles n. Yeah, so it is a beta to the d by m. So there's a kb here which will cancel in this process times d by m plus 1 into f d by m plus 1 divided by beta to the minus d by divided by n, which is okay. So that was the first term. And coming to the second term now, a beta to the minus b by n minus 1 times. So dou by dou z of this is that is that. And finally, we have this expression that we have calculated just now, dou z by dou t. So that is minus d by m divided by f d by m minus 1. I think, yeah, it's just f d by m. Yeah, so finally, and we have to divide with 1 over n. So this will just cancel, and what we have is that Cv by nkb, and yeah, there's a kb divided by kb. Yeah. So simplifying this, we will get d by n plus 1 times, and this term, if we simplify, we will see that it is equal to minus d by m times f d by m of z divided by, yeah. So this is the uh, yes, yeah. So that is the expression for Cv finally. Yeah. So I hope I got all the factors right. But yeah, let me check after the session and uh, make any corrections if applicable. Uh, and I will write uh, the correct expression with all the factors below this in the notes. If there is something wrong here. Okay, yeah, but that is the general idea of making use of these properties of the Fermi integrals, and also uh, making use of the particle equation to find dou z by dou t at constant volume. Okay. uh, all right. Yeah, so now to the next question. uh, so in this problem, uh, we have to calculate the entropy per particle, S by N, of a Fermi gas, and show that it is a function only of fugacity. So the dependence of this on the temperature and chemical potential uh, occurs only as a function of e to the beta mu, only as a function of fugacity. Yeah. So okay, we can just calculate an expression for this and see if that is the case. If and see if we can find an expression that involves only the fugacity. Yeah. Uh, so like we have discussed all this. I mean, like since we have written expressions for EV and sorry uh, E and N and pressure here. So it will be useful to make use of the Euler's relation. So if you remember, uh, so this is something we learned in thermodynamics, which relates uh, the entropy with the energy and particle number and so on. So this, in conjunction with the first law of thermodynamics, gave us the Gibbs-Duhem relation. So just to revise. So yeah, it is this relation that we'll be using. Yeah. So yeah, what is this relation in this case? Yeah, let me just uh, check this to make sure I don't make any mistake. Yeah. So all right. So the relation is like this. So this in sense, Simpsons will uh, I mean this together with the first law uh, uh, gave us a relation between the three intensive quantities P, T, and mu. So they are not all independent, like we discussed. So yeah, anyway, so from this we can just calculate S in terms of U, P, and V. Right, so S is U by, we want S by N, let's say S by N KB. So this thing is equal to U by N kbt plus PV by n kbt is mu by kbt. All right, so z is e to the beta mu. So log z is beta mu, which is mu by kbt. Right, so this term is actually log z. This term that we have here, the last term is log z. Yeah, so we can just do this problem for, let's say, the usual like three-dimensional gas with quadratic dispersion. Uh, so U will be 3 by 2, or PV will be 3 by 2 times PV. Sorry, 3 by 2 times PV is 2 by 3 times uh, E. So U here is nothing but the expectation value of energy. Yeah, so substituting that, we will see that S by NKB is 5 by 3 expectation value of E by NKBT minus log Z. Yeah, so we have to show that this is a function only of Z. Yeah, so actually uh, it is something that directly follows from the expressions for E and N. So if you remember, uh, yeah, so we can just simply use this for our problem also. So E will be, let me write it for this case. So E is going to be A by beta to the pi by 2 f pi by 2 of Z. Again, A is some A is the proportionality constant that appears in the density of states. Uh, and so that is 5 by 2 for energy, and for the number of particles that is going to be 3 by 2. So N is going to be so this ratio is simply kBT times f5 by 2 of Z by f3 by 2 of Z. Yeah, so finally, yeah, there is this kBT here to cancel this kBT. Oops, sorry. Yeah, so finally, what we see is that S by NKB is going to be equal to 5 by 3 this minus log z. Yeah, so this as we see is only a function of z. Yeah, so the entropy of particle, yeah, it can be expressed only as a function of z, the fugacity. All right, so okay, sorry. Yeah, okay, so let's look at the next problem. Yeah, so now this is about the low temperature behavior of Fermi gas. Okay, and we have to find how the chemical potential depends on the temperature for temperature near zero, but not exactly zero. So how does it depend on temperature, and uh, how does the specific heat depend on the temperature? Yeah, uh, so we have learned this from, I mean, in the lectures we have learned this for the three-dimensional gas. But uh, uh, what uh, what we'll be showing in this problem is that this linear dependence of specific heat capacity on temperature, that is not special to three dimensions or the quadratic dispersion. It is it's a property of the Fermi-Dirac distribution. I mean, it's a consequence of the Fermi-Dirac distribution. So the idea of this question is to show that uh, you know the it is the Fermi-Dirac distribution behind this that gives rise to this linear dependence of temperature. Uh, sorry, linear dependence of specific heat on temperature near near t equal to zero. Yeah. Okay. So yeah. So let's discuss what we have to do. So first of all, we have okay. So it is given that there is like some density A of E of A of epsilon of the single particle states, right? Uh, so what we have to do, like in principle, is that there is this particle number equation. Uh, it says that so uh, the idea is that so the as a first step we would have to invert this equation to find the chemical potential, right? So we'll have to find the chemical potential from and then so that would be the first step. You have to show that chemical potential is like this, and then use that to find the specific heat capacity. Okay, so all right, so we have to first discuss the limit in which we are operating. So T is 0, the temperature is 0, and uh, uh, I mean, like when the temperature is 0, the chemical potential is given by mu is equal to EF, and the fugacity Z is equal to beta mu. This goes to infinity. So we have to do a large, we are in the large Z limit. Okay, so we can make use of we can make use of this relation. Uh, I mean this result that we discussed in the first problem, which is the large Z expansion for the Fermi-Dirac integral. Fn of Z is equal to log Z to the n by gamma plus 1 times 1 plus pi squared by 6 n into n minus 1 times by log Z whole square plus so on, right? So this is the expansion we have. And first, let's start with this particle number equation, which says n is integral 0 to infinity te. So here it is given as a of e. So a of e